let's have a little fun here. So if you look on the back page, so on the right-hand side is a big text box. In that text box is what we call a table of reduction potentials. A table of reduction potentials. So voltage or potential is a little bit of a pain in the butt. Everything is relative. We only know what the voltage of something is when it's compared to something else. And so somewhere along the way, somebody came and said, you know, this lovely electrode right here, let's make this the standard. And so when we measure a voltage, it's always relative to this reaction. And they said, okay, let's do that. And this thing, therefore, since everything's compared to it, they gave it a value of 0. And they call this thing the standard hydrogen electrode, the She. You're supposed to know this. When you flip a reaction around the other way, it changes the voltage to the opposite sign. But this one, it's 0 forward and it's 0 reverse under standard conditions. It's not on your sheet yet. So we're going to go there. It's in your table of standard reduction potentials, though, is 0. So I just wanted to point out that voltage is always measured relative to this reaction. And this is the only one they expect you to remember the value of. It's 0. She, standard hydrogen electrode. Electrode, yeah. So standard hydrogen electrode. Cool. So everything's always relative to this reaction being 0. And we expect you to remember that this reaction is 0 for its standard value. So if you look, you've got that table of reduction potentials. Those were all measured where this was the other half of the reaction, one way or another. And so if you look there, I see a number of different reduction potentials, and we use those to calculate the standard overall potential of a given reaction, like this one here, or like this one here. We're going to see where this 1.10 volts actually came from. So take off our diagram. And we're just going to simply break this up into 2 halves. We're going to look at copper 2+ turning into copper, and we're going to look at zinc turning into zinc 2+. Now, if you look at your table of reduction potentials on that second page, one of these half reactions in exactly the order that it's going shows up. Which one? So as it's written left to right, which one matches what's on that chart? Copper does. Copper 2+ turning into copper. And what is the value for that? It's 0.34 volts. Now, the zinc reaction, though, is zinc going to zinc 2+. Now, this is an oxidation half reaction. And what I've provided you with is a table of reduction potentials. Back in the day, some people published tables of reduction potentials. Some people published tables of oxidation potentials. And because it was such a mess, they standardized it and said, you know what, let's just do just reduction potentials. And so most textbooks, that's all they give you. Now on a test, your teacher could give you anything he wants, right? So in this case, zinc turning into zinc 2+, that is opposite of what's on your handout. Your handout has zinc 2+ turning into zinc. And what was the half reaction potential for that? Negative 0.76. So if we're going the other direction, what do you suppose is the voltage potential for that? Positive 0.76. It changes the sign. And then you just add them together. Bless you. And what do you get when you add these together? 1.1. That's where I got that from. I gave it to you from the get-go initially, but you can calculate it from a table of reduction potentials like this. If you have a reduction, great. It's already matching what's on your chart. You just use that value. But if you have an oxidation, it's going to be opposite of what's on your chart, and you'll change the sign. Now, here's the deal. People often think you guys are just stupid. Think all you students are dumb. They're wrong, and you're going to prove they're wrong, but they think you're dumb. There's 2 ways to calculate this, it turns out. You can do that E cell equals E reduction plus E oxidation. Now, were there actually any oxidation potentials on the chart? No, but what did you do to get it? You just found the one that was backwards and made it negative, right? And then you got the oxidation potential, and then we just added them together. Well, sometimes they don't trust you guys to do that. They don't trust you to know when to change the sign and stuff like that. And so sometimes you'll see people instead give you an equation like this one. Now, you don't usually show you that it's just E reduction and E reduction. They usually say cathode minus anode. But they're just using the reduction potentials. They're never changing the sign. They say, we don't trust you to know when to change it, so don't ever change it. But by subtracting, what are they doing? They're changing the sign. So they don't trust you to know when to change it, but if it's the anode, well, that's the one that's oxidation. It'll be the one that's backwards. By subtracting it, they're changing the sign. So a lot of books go here, I don't. I think it betrays a huge lack of understanding. If the reaction is backward, then change the sign. Now here's the deal. Don't screw this up though. If you change the sign yourself, you better add it. But don't change the sign and subtract it. Don't do that. It's one or the other, not both. Cool? But if the reaction is backwards from what's on your sheet, that's the one you change. Cool. But either way, whether you do 0.34 plus 0.76 or 0.34 minus a negative 0.76, same answer. So, but I will not use this last one the whole rest of the night here. Not my favorite. Betrays a lack of understanding, and I really want you to get the understanding because it'll help you on a couple other concepts. So let's look at a couple other reactions here and calculate their standard reaction potentials. So in this one here, we've got zinc 2 plus turning into zinc, and we've got cobalt turning into cobalt 2 plus. Which one of these matches what's on your handout in the table of reduction potentials? Zinc 2 plus going to zinc, and that's got a value of negative 0.76 volts, right? Now, cobalt to cobalt 2 plus is opposite of what's on your sheet. What is the actual reduction potential on your sheet? So 0.28 or negative 0.28? Negative 0.28. But because we're going backwards, what do we have to do? Change the sign and make it positive 0.28 volts. And then add these together, and what do we get for the overall standard E cell? Negative 0.48 volts. That table's got to be given. You do not have to memorize that table at all. It'll show up on the, for you guys, it'll show up on the front page of your exam. So you just got to know where to look for it and that you need to look for it. So if we look at this next one. So in this next one, so if we look at this sec, before we actually calculate the voltage, let's say we were calculating delta G and we had delta G's of formation. What would we do with those delta G's of formation values? Products minus reactants multiply by the coefficients, right? For delta G, delta H, and delta S, the coefficients totally factor in, but not for voltage. We're going to ignore these coefficients completely, as we'll see. Don't factor into your voltage at all. So if we look, chromium 3 plus going to chromium, is that what's on your page, or is it backwards? Oh, let's get this right. That looks terrible. So the chromium 3 plus to chromium, that's the way it goes on your sheet, right? So that's a reduction. So what's the value off the sheet for that? Cool, negative 0.74 volts, okay? Now, copper going to copper 2 plus, that's backwards, right? And if the forward ray is positive 0.34, then going oxidation backwards should be negative 0.34 volts, and if we add these together, we get standard value under standard conditions would be negative 1.08 volts. Would that be spontaneous under standard conditions then? No, wouldn't be spontaneous at all. Cool. These are some typical questions. Just calculate standard potential or standard cell potential for a particular reaction. Great. We can totally do that. So, well, the voltage is negative, and if you recall, we said, what do you want delta G to be for a reaction to be spontaneous? Negative. But what do you want the voltage to be? Positive for a spontaneous reaction. And we'll go over that one more time here in a little bit. Okay, here's the deal. A volt is a joule per coulomb, it turns out. A joule is a measure of energy. It's where delta G is measured in oftentimes, right? A coulomb, you ever heard of a coulomb before? Coulomb is a measure of charge. So it's a measure of charge. Like electrons have a certain charge in coulombs associated with them. So in this case, when you, let's say I doubled this reaction, I doubled the whole reaction, what would happen to delta G if I double the whole reaction? Well, delta G would double. The joules would double. But then twice as many electrons would be involved, and so the coulombs would double as well. And if the joules and the coulombs both double, then what happens to the voltage? Not a single thing. And that's why the coefficients don't factor in for voltage. They will for delta G or delta H or delta S, but not for volts. Cool? Okay. Last question on this section on your handout there. It says, what is the balanced reaction for the galvanic cell composed of Mn2 plus and Fe2 plus? And let's write these out. So if you recall, what kind of reaction is this entire chapter based around? Redox, which stands for oxidation-reduction reactions. You ever heard of a reduction-reduction reaction? Nope, doesn't exist. You ever heard of an oxidation-oxidation reaction? Nope, doesn't exist. It's all about oxidation reduction. You have to have somebody lose and somebody gain electrons, so the electron transfer. So here's the deal. This question is in principle different from the previous two. The previous two questions, you were given the complete balanced reaction and said find the E cell. Great. But this next one, you were just told the manganese 2 plus manganese and the Fe2 plus Fe system. Find the galvanic cell associated with that. In fact, let me get the exact wording here. It says, what is the balanced reaction for the galvanic cell composed of Mn2 plus Mn and Fe2 plus Fe? They told me it's galvanic, which means what has to be true about the voltage? It's got to come out positive. Did these have to come out positive? No, obviously they came out negative. What's the only reason I know this one's going to have to come out positive? What's the key word in the question? Galvanic. That's the only way I know. Question? Cool. Yeah, this is a half of a reaction, and this is a half of a reaction. We got to combine them into one overall reaction. Now, is this oxidation or reduction again? These are both reduction. Electrons are gained, came off the table of reduction potentials. These are reductions. If I'm going to do redox, oxidation reduction, then I can't just add these together as they are. I got to make one of them backwards and be oxidation. The question is, which one? Well, which one can I flip, which changes the sign, and still come out with an overall positive voltage? Yeah, the top one. If I flip this, I'll have positive 1.18. This will still be negative, but I'll come out with an overall positive voltage. But notice, what if I flip this one? That would be positive 0.44, but this is still going to be negative 1.18, and it's not going to come out positive. Because we're told that it's a galvanic cell in the question, we got to get a positive voltage. And so in this case, we're going to keep the second reaction as it is, but the top one's going to get flipped. Manganese metal will now be the reactant, and manganese 2 plus will be the product. And the overall E cell would be negative 0.44 volts plus positive 1.18 volts. And you don't even actually solve it out. You just know that, yeah, now it'll come out positive. I flipped the correct reaction around, or the correct half of a reaction, rather. Cool. So a little bit different question than the previous two, but based on the same principles.